this solid-state spin-based sensing or quantum gravimetry. So I request, sir, please cover this topic. And if anything is missing or have you already mentioned yesterday some topics, so you may cover it. So once again, thank on behalf of our academy and MNIT Jaipur for accepting my invitation and available throughout this program. So without any further delay, I request Aswa sir, so please take over. So right now, I think 145 participants have already joined. Thank you,
Yes,
sir.
sir. Thank you, Avasti sir. I was thanking you, but I should express my sincere gratitude to you for giving me the opportunity for such a vast number of concepts to discuss and my whatever my understanding to convey to the participants. I would not say teach because uh, I have not reached that high level of understanding of every concept which I discussed so far. Whatever my understanding, that I just try to convey to the participants. So along the way, probably I also got so much of insights and understanding, and improved my understanding on the concepts which I touched. Right. So yeah, yes, sir. So right now 203, we can wait for a couple of minutes and go ahead. Like you mentioned, I would cover both the topics, solid state based sensings and as well as
Quantum
this,
gravimetry.
yeah, gravimetry. So yesterday, participants, I think, if I remember correctly, they were asking to discuss about squeezing of a light as well as quantum tunneling. I will touch both the topics. So, in fact, the squeezing of a light is required for this quantum sensing. Okay, and moreover, it is required to understand even the parts of what I should say, single photon generation, which is backbone of all the sensing, right? So in that way, we will make it more complete and touch all those things. Yeah.
Yes.
Okay, so 170 plus participants. So maybe a minute. Okay, one more minute. Yeah, I think we can start.
Sure, sir. Please.
Okay, hello everyone. A very good afternoon to all the participants. All right. Yes. So as you can see, the title of the discussion for today right now is light and its squeeze states, and this is a part of quantization of light, and we'll try to give some physical interpretation for the squeezing part. Okay, I did add a nice figures where you can just see. Okay, right, in the first slides itself I have written something called coherent states. Okay, coherent states, and then phase squeeze state, amplitude squeeze state, vacuum state, and squeezed vacuum state. Okay, so looking at all these four figures, you may not get the exact picture right now. Okay, but as we go through this the short presentation, you would really appreciate what is mean by squeezing of light. Okay, right? And after finish of this, I will discuss something called tunneling also. Okay, right? Okay then. So let me go to the next slide. As you know, right? So light is usually represented by electromagnetic wave. Okay, so light do possess electric field vector and magnetic field vector in that. That is what the EM wave is. Okay, here I have only the light represented in terms of the electric field vector which is oscillating. For example, the electric field vector which is oscillating here is shown in the color of yellow. Okay, so what is happening is, see, the electric field vector is initially, if I just draw that yellow color separately, let me take a yellow color. Okay, yeah, let me take yellow color. Okay, maybe thickness slightly more. Okay, right. Now what is happening is, light intensity is dictated by the strength of its amplitude, or any wave intensity is dictated by its amplitude. You see, the amplitude of the wave is small, more, increasing, and then decreasing. But the amplitude is fixed. Why it is increasing and decreasing is the amplitude multiplied by the phase factor. Okay, as time progress. Okay, let's say this is a phase constant. If I take step to 0, so it starts from at this point t equal to 0. Okay, if phase factor some constant is there, the wave might start before t equal to 0. That is what this phase constant would decide. So the electric field vector, the E, is oscillating its strength. The overall strength is oscillating, means increasing and then decrease. See, it becomes 0 at this point and then decrease. That means negatively it increases and goes maximum. Okay, negatively decreases and becomes almost 0. And then now it is increases its oscillation by going maximum. This is what the electromagnetic wave is. Similar story would apply even for magnetic fields. Magnetic field is, okay. So the magnetic field is existing. Okay, it is going to exist in the plane of, okay, right. Let's say the propagation is along the x-axis, z-axis is towards us, and y-axis is upwards. Okay, right? So now the magnetic field is oscillating in z. It is oscillating in which plane? It is oscillating in z and y plane. Okay. How it is oscillating? It is oscillating like, so here they're shown is towards us it is oscillating. For the simplicity, I just give it like this. It is oscillating like this. Okay. So here the magnetic field vector B increases and then decreases, increases in the negative, increases in the positive. So this is what electric and magnetic field vector behaves in electromagnetic wave. Okay, fine. This is a classical light for you. Okay, what I mean by classical light is, I'm not talking in terms of light being quantized, light having a particles of photon. I'm not talking. I'm still taking into consideration that light can increase continuously and decrease continuously. Okay, right? So here I have a deterministic amplitude and phase. So E naught is fixed and there is oscillatory phase, means this part decides that phase. Okay, right? Okay, what else I have here? Okay, let me write down this phase constant. Phase constant. So this entire thing is phase. So inside a phase, I have a phase constant phi is equal to 0. Okay, considered. You can consider or not consider, it's up to you. Okay, so energy is continuous, no quantumness here. That means I will not think that light is consisting of photons. Okay, right? So there is no quantumness, no quantization there. And if I do that, this will play this kind of a assumption or an idea fails to explain the phenomena like photon counting statistics, short noise and vacuum fluctuations, and squeeze light and anti-bunching. So we have seen, okay, right? So let me take that. Okay, let me take that quickly. That which we discussed last time. Okay, let me show you. I have that with, at this point. 1 minute. Where do I have here? Okay, I don't have it here. Let me show you. So what I want to show you is 1 minute. So one minute. Yes. Okay. This is what I want to show you. If I just take a classical light, thermal source. Okay, if I induce the quantization, what I see, the photons being clubbing together, sometime separating out. It's called bunching and anti-bunching. Okay, but in the case of coherent light, bunching happens very, very neatly, and I see there is a sequence of bunching and not bunching, anti-bunching. So in the case of single photon sources, I don't see any bunching at all. The single photon sources are, okay, they are, this is, okay, so 1 minute. Yeah, the single photon sources are very special forces. They are actually called Fock states. Okay, the Fock states are more useful to generation of single photons, but in the coherent states, still I can generate single photons. Okay, but there is no guarantee that every time I get a single photon, I might get a bunch of photons, means paired photons. Sometime I have to disregard. So this is actually the bunching and anti-bunching process takes place in the case of thermal source, the classical light, in the case of that is conventional light, in the case of laser light. Okay, right? So now let's get back for our case, which is right now. Okay, this case right now, if you see, okay, where were we? We are here. Squeezed light and anti-bunching will not understand or not able to accept if I have not considered light as a quantized unit. So the quantization is not there. I would like the concept would fail to explain. what is these important processes. Okay, right? Fine. Okay, let's go further. Okay, so it's very important to have light to be considered as a quantized field. Okay, right. Now the question is, light is quantized field means what? It is, there are particles of light which are photons. So these photons could be treated as a bunch of harmonic oscillator modes. Okay, so electromagnetic field is treated as a harmonic oscillator modes. Now, like discussed a long time, the modes is something when it comes to harmonic oscillator means simplest harmonic oscillator is started with the simple pendulum. Mode of oscillation is like this. Another mode of oscillation is towards us, away from us for a single pendulum. Okay. Similarly, for a spring mass system, okay, only one way of oscillation is possible, that is going back and forth, or if it is allowed to go left and right, it will go in that way. Probably I'll have extra dimension. Okay, you just think that that is what the simple pendulum. Now an electron, I can straight away understand electron goes around the nucleus. It's a nice pendulum, oscillatory pendulum for you. And when it comes to electromagnetic wave, what is oscillating? Right? That's a question you usually will ask. This is simple pendulum. Okay, simple pendulum. So in the case of light, okay, so we talk in terms of various modes of oscillation or various modes of dynamics in terms of the way disturbance travels through, where the way energy travels through the space. So that is what the mode of oscillation. So for example, if there is a space between that, I will send a light. So the light can exist in a mode of oscillation, something like within the space I can have only one wavelength, half a wavelength confined. Okay, this is a mode 1, or I can say mode 0. In another case, I can have light make one complete wavelength. Okay, one complete wavelength. Okay, I'm making a mistakes again. Yeah, one complete wavelength it makes. And since it is there are ending at the edges, probably it creates a standing wave pattern. Just like you tie a thread at the edges and then create a disturbance, you will have a mode of oscillation. So this is another mode of oscillation for light. So I can keep going, increase the number of wavelengths confined. This here I have 1.5 wavelength. So I am 2. So likewise, I can have any combination of different ways of mode of energy travel. So these are the mode of oscillations. These are like mode of energies with which light exists. Let's say this has some energy, some frequency mu, which is converted into energy h mu. So E0 is h mu. E1 would be some, let's say h mu naught, h mu 1. Okay, so in terms of harmonic oscillator, if I start expressing this modes of oscillations, see this mode of this is like the electron existing the most ground state. The second one, electron exists in the excited state. Similarly, a photon being existing in a mode 0, a photon being existing in mode 1, and so on. So these modes are the various states of harmonic oscillator. So those harmonic oscillator, not only one, remember there are many modes are existing. So many modes of harmonic oscillators would exist in a light quantized light. So there Hamiltonian of that light is represented as this. Remember, in the simplest form I am writing, I am not considering many modes. Okay, I am not considering there are modes, there are propagation vectors, the direction in which light travels. All those things I am just generalizing into one simple scenario. So in that simple scenario, so harmonic oscillator is written as just in terms of annihilation and creation operators. The moment you write H as that, okay, now remember the field operator. Now there is a confusion. The electric field is also written with the E. Energies are also written with the E. So what you do, probably you might say En. En stands for energy and E stands for electric field. Okay. Now, just now we saw for a classical light, electric field is just a sinusoidal function, E naught cosine function, E naught cos omega t plus phi. So, in with the moment I introduce the quantumness, means quantize the light into photons, the representation of the electromagnetic light, electromagnetic wave. So electromagnetic wave was a vector E naught cos omega t plus phi becomes electric field operator. So what is this operator would be? This operator would be consisting of amplitude, but inside a phase, whatever is the phase is there, that is converted into creation and annihilation and creation operators with some exponential minus I omega t, where omega is the angular frequency of the light. Now the question you asked me, how did you get this? Okay. So going from here to here, how do we get? I can give you a hint, remember, okay? I can give you a hint, but the derivation is not that straightforward, okay? So it requires a little bit of more digging deep, okay? So as a time being, you can assume that we have straight away got that answer, okay, right? So who is somebody who is not accepting straight away this expression, for them I can give you a shorthand hints. How do we get that? Okay, right? So how do we get that is, usually how did we get to this level? From the actual Hamiltonian. Okay, let's bring it back. The actual Hamiltonian of an electron, for example, okay, actual Hamiltonian of an electron, let's say, okay, actual Hamiltonian of the electron is what? H operator is p square, where p is the momentum operator, by 2m plus, okay, some potential energy, which is a function of position and time. Okay, right? Or you can write in terms of q. Q stands for position operator. Okay, so this is what we have, where p takes the form of minus ih cross dou by dou x for the x dimension. If I do this, Hamiltonian operator in x dimension is minus h square dou square by dou x square. Okay, I have by 2m, okay, plus the position of potential energy operator. Okay, this is what I have. Now, since it's a quadratic in nature, differential equation, what we do? We introduce a small momentum operator, scaled version, P and Q in terms of capital P and, okay, in terms of what did I use here? Some, okay, this is x, I'm sorry. Okay, let's put this as x. Okay, capital X, right? The moment you introduce, the quadratic nature still there, but I got rid of the extra factor of m and h square, all those, sorry, m and all I get rid of. So the Hamiltonian this time would be, okay, p square plus q square by 2, I think, into h omega, if I remember correctly. This is what I have. Now what we do to get rid of this quadratic nature, we introduce the annihilation operator, which is PQ plus IP, okay, divided by square root of 2, and A dagger is Q minus IP divided by square root of 2. The moment you introduce this, what Hamiltonian would become? Hamiltonian would become simply A dagger A plus half multiplied by H omega. You see, simple it becomes. Now, what it is conveying is the electron would exist in the ground state with energy H omega naught, exist in excited state with energy E1, and second excited state with energy E2, and so on. The electron would exist at different energy levels. So this is a quantization states of quantized states of an electron inside an atom. Okay, right? So you study the eigenvalue equation. H psi is equal to E psi, energy psi, and you would get. Okay, so from there you get. Now you use this idea. Just use this idea here. Where is this idea? Here in this case, right? Yeah, here in our case. And please see, the moment I introduce such a notation for electromagnetic wave, okay, the energy of the system becomes a similar way, but where the electric field vector, which is having some angular frequency, that term is expressed as some creation and annihilation operators. Okay, right? So understanding exactly how we get to this point is another zone of physics branch. So we have not take that into consideration because it itself takes 1 or 2 hours derivation. So you please assume that electric field vector becomes like this, where creation operator is there, annihilation operator is there. So what is the effect of the creation annihilation operator? Let's say there is a state where one photon is there. Let's say there is a photon. There is a photon is there. Okay, wait a minute. Let's say there is one photon is there. If annihilation operator acts on that photon, what happens? It just suppresses the photon, removes that photon, converts the quantum state to have no photon at all. So this is called a vacuum state. Means nothing is there in that state. Already one photon was there inside a box. So I sent the annihilation operator. It sucks the photon energy out and it just annihilates and nullifies the photon and has no photon inside the box. The effect of creation operator is, let's say I have a zero photon inside a box. If I have creation operator acting on this, what happens? I would get 1 into 1. So this is, I would get a single photon state by just added up by annihilation creation operator. So creation operator is like something which adds energy to the system by adding a photon. Okay, fine. So very good, that I got now. Fine. So let me go further. Now, if I just take a light, okay. So light is distributed in space, like in dimensions, x dimension, y dimension, z dimension. Okay. So I can measure the light and specify in which direction, what is its strength and what is it there. Okay. Right. So you looking at the electric field distribution here, if you see it is having annihilation and creation operator, light should be not only just described in the space x and y and z space. Light should be described in, there are something called two phase dimensions, sorry, two dimensions. Those dimensions are actually constructed out of creation and annihilation operators by taking their sum and by taking their separation or a difference. So there I am going to construct something called quadratures. Okay. So what I mean by quadratures are, I take the light, let's say light is in some state, let's say number of photons are there. If I add a quantum operator x1, let's say some quantum operator, what it is going to do, it is going to give me some number, okay, some number, let's say some x1 number and the state. Let's say n is a happen to be a quantum state of that x1 operator. So it is just like a thermometer with a scaling. I use to the patient, I'll find the temperature. So X1 is something, some kind of a probe which going to measure the light and going to tell me what is the state of the light. And similarly, I have one more operator X2, which is also going to give me some X2 value, act on the light state and gives me some X2 values. Okay. These are like a simple probes which measures the state of the system and tells me about what is the system is actually made up of, in which state it's existing in. So just recollect back, okay, a few things we discussed. If in the quantum level, you see, classically, okay, our dynamical systems are described by position, momentum, okay. So x and p are enough to describe, okay, dynamics of a classical system, okay, right? Classical system means a macroscopic system which is moving, macro. But when it comes to quantum, what we would be doing is not only a position operator, not only a momentum operator, we would also talk about spin operator, angular spin, rotational angular spin, okay, and the quantum numbers, which orbit system is existing, what is the shape of the orbit, S, P, or D orbit or F orbit. All those things would tell me more about the electron or a quantum particle and its existence dynamically. Okay, so quantum observables, they call quantum observables, are operators needed to describe the dynamics of the system, dynamics of quantum system. Okay, I would say that. Fine. Now, if you get back our case here, the x1 and x2 are such observables which probe the light in quantum form and tells me about what are the states the light is existing in. So this x1 and x2 are constructed out of annihilation and creation operator. And remember, in the case of quantum system, if you just take x operator and p operator, okay, if you just try to find their commutator bracket, which is in fact equal to I, okay, it's non-zero, non-complex I, which means xp is not equal to p into x. You know why? xp is equal to x into ih cross minus ih cross dou by dou x acting on 1, which is 0. Px is minus ih cross dou by dou x acting on x, which is going to give me ih cross minus ih cross. Now the difference of that, okay, right? This is 0 minus of minus ih cross is equal to ih. We should not forget Planck's constant. Okay, so x and p are anti-commutator operators. They never commute, and they are also called incompatible. Incompatible operators. Means they're not going to work in sync. Because of that, they always fight when it comes to measuring perfectly. Any error in position, any error in momentum, if you calculate, which is always going to be greater than Planck's constant divided by 2. Okay, h cut by 2. So if you increase the accuracy in x, you have to compromise accuracy in p. If you increase the accuracy in p, you have to compromise accuracy in x. So that is what incompatibleness of the measurement between these two operators. Now in our case, in the light case, I am going to construct two incompatible operators. See, light, the position and momentum may not be the right thing. So they have introduced a new operators, annihilation and creation, A consisting of P and Q. Okay. And A is contained in x1 prime, x1 and x2. Okay. Now if you cross check, the commutator between x1 and x2 is obviously not equal to 0. They're incompatible, and that value comes out to be I by 2. By the way, how did I get I by 2? As you guys know, the commutator between A to A dagger is, I think, 1. Okay, I think I have it somewhere. Do I have it somewhere in the notes? Okay, we did it earlier. Don't worry. You can just, yeah, you can just take it for granted. Okay, fine. We have done this, I think. Yeah, I think we have done this. Now, using that, as you can see, you got commutator between and x1 and x2 is equal to I by 2. Okay, and if you could see this one, it's just a constant, and this is like a phase, like which is having a complex I in it. So this is like a complex number. So complex numbers are usually associated with phase of a system, and constant, right, scalars are associated with the amplitude of a vector. Okay, so this is like magnitude of a vector, and this is like magnitude means amplitude. This is like a phase of a vector. Okay, looking at the way they are constructed. Now, since they are incompatible, you can always find what is the error in finding delta x, what is the error in delta x2, which is comes out to be greater than equal to 1 by 4. Okay, remember the way to derive this is a similar to uncertainty principle. Okay, uncertainty principle for x and p. Just like that, whatever we did it for uncertainty principle, in the same way, you can derive what is the uncertainty in the case of x1 operator and x2 operator on a light. Okay, right? So we'll not get into the details of how did this is done. If somebody wanted to know, I can share the material, my notes, you can go through it. First of all, if you understand how you get delta x, delta p greater than h by 2. If you understand that, you can getting this is straightforward. Okay, right. Now let's go for that. Now, light is existing in classical light form. It can exist in coherent light form. It can exist in Fock light form, Fock states. Okay. The coherent light source means a conventional light source. Can't quantize the source. I treat the light as continuously varying. That is not of my big interest when it comes to quantum computing. Means I have not done the quantization of the light, so I don't bother. The next one is coherent light source. What is a coherent light? Coherent light is represented by alpha kets. These are eigenvectors of annihilation operator A. Okay, right? They are laser light dynamics. Okay, dynamical states, let me say, right? Now, a laser light source, if you notice, if you carefully notice, and as eigenvalue equation represents, A acting on alpha gives some alpha into alpha ket. Remember, alpha is constructed from, okay, the Fox states. Okay, so alpha is constructed from the number states, is also called Fox states. Fox states mathematically, but when it comes to physically, just a laser light source. Now, on the light source, if you act x1 operator to measure the character and x2 operator measure this character, okay, it's like thermometer I use and find the temperature of a person, and I also use the pressure measuring tool to find the blood pressure of a person and see what is the status of the patient. And along the x direction, let's say x1 is, let's say x1 is the values of output I measured when I make a x1 operator action on the light which I have made the measurement. Okay, basically what I mean, x1 acting on alpha state giving me some x1 alpha state. Okay, x2 acting on alpha state giving me some x2 alpha state. So x1 and x2 are the values of information I got about the light. Okay, now always x1 and x2 are incompatible. What happens? How much error I would do when it comes to x1 measurement, when it comes to x2 measurement, if I find, interestingly, what do I find is the errors are same, equal in both in the x1 direction, also in the x2 direction. By the way, what is x1? Looking at the construction the way x1 is done, it is a scalar, it's like a magnitude. The x2 is like a phase. Okay, right? Now, if I just plot, okay, so if I just plot various x values I got, let me different color it. Various x1 colors if I plot like this, various y1, x2 values if I plot, you see the blurredness along the x direction, x1 direction, blurredness along the y direction, both are same. Okay, both are exactly same. Literally to be said, so I should be getting a single point result I should be getting. But what I am getting, it's like error is say I'm supposed to get exactly x1 and x2. But since the system is having quantized, there is a noise in the system. Even the laser light is a noise, having noise. The light coming out, interacting with the surrounding. If I just take some kind of a sheet, a paper, and put the laser light, it should be a single spot. But around the light, I see some blurredness. That is the error, okay, while seeing the light. So the error is along the x1 direction, along the amplitude direction, and means x1, along the phase direction we see both are exactly same. Okay, very good. Now, okay, so what is the product of uncertainty? Product is, so usually delta x1, delta x2 must be greater than greater than 1 by 4. 1 minute, greater than 1 by 4. 1 by 4. Okay, 1 minute. Least value is 1 by 4. I got delta x1, delta x2 both are equal to half. I got overall product is 1 by 4. So that is said to be minimum uncertainty state. The coherent light state is the minimum uncertainty state. Okay. Now, the classical light represents a laser output with a minimal quantum fluctuation. Okay. Now, let me go and do some kind of a, let's say I don't want accuracy in particular phase side. Okay, or I want amplitude. I don't care about amplitude accuracy. I more care about the, wait a minute, why this is, okay, 1 minute. Yeah, this was cut, I think. Yeah, this was cut. Okay, so what I mean is this is a delta x phase. Okay, so I want more accuracy in delta phase, less accuracy in amplitude case. So what should I do now? I have to reduce the error in x1 and let it be error in x2 can go high. What I mean is error in the one of them can go high. Here in this particular case, x2 stands for phase, x1 stands for amplitude. Okay, whatever figure I have here, it is opposite around. So in this case, amplitude is increased in the error. Okay, accuracy is increased in the case of phase. Okay, so this is exactly opposite whatever I have given. The figure is like this. Okay, now how it is possible? We will do some kind of a squeezing operation. What is a squeezing operation means? We will take care of accuracy in one of the dimension, amplitude dimension. We let it go. The accuracy in the other dimension can increase because it is incompatible. They are connected each other. So for an operation to reduce the noise effect in one of the dimension is done by, on paper it is represented by something called squeezing operator. Okay, so what is the squeezing operator is constructed about? It's constructed with, again, okay, it's constructed with using annihilation and creation operators, the square terms, and also it's an exponential term, and there is a parameter, something called R parameter. It's called squeezing parameter. Okay, that parameter would decide how much squeezing I should do, which dimension I have to reduce errors in that dimension, and in the other dimension increase the errors. Okay, so that is what, when let's say if I just take r equal to 0, I'm not acting any squeezing operator because this comes out to be e exponential 0, it's 1. The squeezing I'm not doing. Let's say r is equal to some stronger large value. In that case, what happens? Delta x variance in the x1 measurement comes out to be 1 by 4 exponential minus 2r. Error or the variance in x2 measurement comes out to be 1 by 4 exponential positive 2r. Right? You see, this is just exponential. This is a quantity which is much smaller. This is a quantity which is much larger when r is large. Okay, when r is large, what happens? This is a 1 over by exponential to r. So denominator increases. Some value 1 divided by large denominator means delta x1 will be, okay, delta x1 will be very small. Very small. How much small? It is less than half. And obviously this one is a large value which is more than, okay. So if I plot the characteristics of the light on phase space constructed out of x1 and x2, phase space means just a dimension, x dimension, y dimension in a two-dimensional surface. Similarly, x1 and x2 are the two dimensions which describe the light source. For a light source, what are the two degrees of freedom for the light? The amplitude with light increase and decrease, with what phase it increase and decrease. Okay, so when I have light as amplitude and phase, okay, so the amplitude is 1 degree of freedom, the entire phase is another degree of freedom. So x1 and x2 stands for those observables. One observable measures the amplitude, another observable measures with what phase the light would exist. So errors in x1 and x2, If usually I have to get exact x1 and x2 values, exact amplitude and phase, but it is not. I get some blurredness around, some fudginess around. So the fudginess is constant, same in the both the cases. That is makes sense. But I sometimes what happens? I want to reduce the fuzziness in the case of phase. Okay, let it the fuzziness goes, ambiguousness goes large in the other case. So that is what I have discussed here. Okay, see the fuzziness in the case of phase is reduced here, but fuzziness in the amplitude got increased, elongated. So this is called a squeezing light. So what is squeezed here? The percentage of error in measuring, the accuracy in measuring got altered in one of the dimension. In another dimension it may go high, in one dimension it's low. That is the squeezing of the light for you. Okay, right? Now when it comes to application, physical interpretation, squeezing redistributes the quantum fluctuations. Okay, quantum fluctuations in the sense the quantumness, quantum features are going to be redistributed, means the noise in one of the dimension is reduced, means not it can't be just completely destroyed, it should go somewhere else and appear somewhere else in other case. Just like uncertainty principle in position and momentum, if you try to find a moving object accurately, you are compromising in finding its momentum, but means the momentum error would increase. Same story is applied here. Squeezing redistributes the quantum fluctuations. Okay, and reducing noise in one variable, that is amplitude, improves the precision, but phase uncertainty increases correspondingly. See, you see what I meant? If you try to measure the amplitude perfectly without any error, what happens? You want to reduce the error measurement to be much smaller. Okay, so let's say smaller. Okay, you want to make it smaller. I don't know how much exact value. I'll say reduction. You want to reduce, but what happens? The phase, this quantity goes high. Okay, error in this quantity. I'm sorry. So omega t plus phi is a phase and phi value is a phase constant. Remember that. Okay. Right. So this is useful for gravitational wave detection. Okay. LIGO stands for that, gravitational observatory. Okay. GO stands for gravitational observatory. And it is also useful for the case of quantum communication. Which kind of light I am generating to do, let's say, transportation, quantum teleportation, and then go on to do quantum key distribution. Okay, in all those cases, what kind of a light I'm just creating, I should study that. There, this squeezing of a light comes to be very handy. And even for quantum metrology, okay, studying the material properties using the light, a material would respond to what kind of a light source and what is its response. For that, it is going to be very useful. Okay, right. Now the question is, how do I realize the experimentally the squeezing of the light? Okay, so people take a non-linear crystals. What is a non-linear crystal for you is, first of all, understand what is a linear crystal. Linear crystal is, let's say I have a medium. Okay, right. So if I apply an electric field, okay, onto this medium. Okay, sorry, I'm sorry, not a mirror. Okay, if I apply electric field, let's say a positive plate and negative plate, what happens? The positive charges would creep out, pushed out, negative charges comes out onto the top. So this is a polarization is happening. So the polarization is directly proportional to the applied electric field. This is the usual property of dielectric material. Now, by any means, if the polarization, the result, the consequence of the system, if it becomes dependent on not only on A, it can depend on second order of A or third order of A and higher orders, This is called non-linearity of the system. Non-linear system. The response of the system depends on the higher order electric field strengths is going to be called non-linearity of the system. The materials which show this kind of a behavior are called non-linear material. Okay, so non-linear crystal. So now if you take that such non-linear materials, I am not going to apply electric field by putting electric field plates or plates. What I will do, I send a beam of light onto this material. You know, electromagnetic wave consisting of electric field vector oscillating, magnetic field vector oscillating. By the way, by using electric field like a plates, I am inducing electric field lines from top to bottom. Na? So instead of sending up, like putting inside a plates, I'll just send a electromagnetic wave. So that is what I am just sending as some pump field onto a non-linear crystal. Non-linear crystal. And now beauty of these systems are, because of this non-linearity, if I send a single frequency, let's say 100 joule frequency, if I send, what happens, you know? Interestingly, I would get some 40 joules of set of photons and 60 joules of another photons. With one single photon get divided into two photons, where one photon is of 40 joule, another photon is 60 joules. So overall energy is conserved. 100 joule energy photon comes in, divided into two photons of two different energies. Okay, so this is called a three-wave mixing. It's called three-wave mixing, and also it is called photon parametric down conversion. Okay, why it is possible? It is possible because the polarization of the material, means the way this nonlinear crystal responds to the incoming electric field, is dependent on the strengths of the electric field. Not only linear, it depends on higher order terms, which is up to E2 onwards. So the chi2 which is there, it's called susceptibility or dielectric susceptibility. Yeah, chi term. Okay, so chi has orders of zeroth order, first order, and second order. Zeroth order means there is no dependency. The first order means linear dependency, linear. This is quadratic. I can have any higher orders also. This the third one is higher order. Okay, where is that? 1 minute. Yeah. Okay, so chi3 is a third order. Now, what is the difference between chi2, chi3 is? Now, I think, do I have a figure for the chi3? No, I don't have. Let me draw myself. So, chi3 is, okay, so I'll have a system. Okay, I will have just a minute. Let me, okay. Yeah, I have a system. Wait a minute. Okay, so here I have two-level atomic system, or I send a pump field, I get back three frequencies. So one is for a pump field, I get idler signal or something like, let me write down omega 1, omega 2, omega 3, where sum of omegas is equal to omega p. Right? So usually people take a signal idler. These are like to ensure to have the splitting of single photon to multiple photons. See here, to have a splitting of single photon to multiple photons, what they do, they will take a pump field, along with they will send some small signal along with. So this will trigger the emission of 40 joule photon. Okay, right? So this is how these people will ensure the conversion of single photon to multiple photons, right? I can have two photons from a single photon. I can have three photons from a single photon. This is actually called the way of realizing or way of obtaining required photon of energy from some default photon having some energy. Let's say I want to have 40 joule photons coming out. So I have a system which is source of 100 joules. Then how should I do that? I use a parametric down conversion, use some crystals, non-linear crystal. I'll get the required 40 joule photon. Okay, that is a signal required. And idler is something which I don't want. So it is idles out, means separates the 100, it separates the 40 joule photon from the pump field, so that I get the 40 joule signal photon. Okay, right. So now the applications. Okay, I think this is the last slide, I guess. Yeah, this is the last slide. So quantum metrology sensing I mentioned already, cryptography, continuous variable quantum computing. Okay, so not only just discrete discrete variable case, I can also do continuous variable. Okay, so summary is given. You can just go through and just to understand, I added a summary. Now this is about the squeezing of the light. I hope you people understood. If there is anything, any doubt, I will just go through. Now, let me see some questions. Okay. Before taking a break, let me try to clear if there is any doubts. Can you please explain the instrumentation part, experimental setup for conversion of normal light with which is a part of EM to quantized portion physically? Could you please explain the expressions of these variances? Okay. Right. So remember the question Lakshmana and Lakshmana is asking is, how do you take a classical light, okay, conventional light, you mean, yeah, normal light, that is a EM wave, to quantized portion. Okay. So normal light, if you just take light coming from a conventional light source, it is no more coherent. Okay. So there is a one ray is coming in one direction, another ray coming in another direction. I can't have quantization possible there, because light rays are behaving differently. So quantization is possible when I take a light source which is having some coherence, means some streamline like a laser source. There, let's say light is appear to be continuous. I use filters like attenuators. In that way, I just reduce the number of photons going through them, and I will get few photons which is quantized form. So that is what I mean when it comes to experimental. When it comes to the theoretical representation, you represents the light in terms of harmonic oscillators. That is the idea. Okay, right? So where is that? Yeah, here. Okay, so light becoming a continuous waveform to discrete form is a conversion from classical form to quantum. Okay, right? So for the sake of, you can't go light from quantum to classical to quantum. It's not possible. Okay, because the conventional light is a classical light, but when you have a coherent light source from the laser, it is already quantized, nicely streamed, so that is suitable for studying the quantization of the light. Okay, and Dr. Arindam's question is, could you please explain the expressions for these variances? Okay, good question. Right, this is what you are asking. By the way, what is the variance? Okay, let me use. Okay, first of all, there is a x1 variable, there is a x2 variable. Okay, there is a quantum state psi, a light state psi. I take this measure, do the measurement on both of on the same state. When I make a measurement on psi, let's say I'll get some values like x1 0, x1 1, x1 2, and so many values. Let's say x2n I'll get. Sorry, x1n I'll get. Okay. Similarly, here also using x2 variable, if I make a measurements, I get x20, x21, x2n. I'll get. Now, if I ask you what is the average value of output when I make a x1 measurements on the side, what you do? You sum all the x1 i's divided by n. Okay, right? This is the expectation value of x1. Similarly, what is the expectation mean value of x2 is sum of all the measurement outputs divided by total. Okay, n values are there, n measurements are done. Now, a given measurement value always deviates from the average value. What I mean is error usually represented, okay, error is usually represented as is equal to x1 measurement minus and its expectation value. Okay, expectation value. This is a deviation from the expectation value. So, how much it deviates on an average for all the calculations? If I ask, what people do? People find the expectation value of the deviation. What is that? Expectation value of the deviation, which is comes out to be, okay, this quantity. If I find this quantity, which is going to be x1 minus okay, this is what the variance is. Variance. I think is there a square root? Something, yeah, something like this is a variance. So this variance is delta x1. Okay, I'm sorry. Yeah, delta x1. I think this is equal to delta x1. Okay, so I'll have delta x1 and delta x2. From there, I already know what is the x1 operator is a operator minus a dagger by 2. x12 is a operator plus divided by 2y. I think this is the expression we have. Okay, yeah. Okay, first one is positive, second one is negative. You can take either way, it's not an issue. Okay, right? So I can act a operator or a dagger operator on side. So what I am doing, I am just taking their positive sum and negative sum, and I'm creating a new operators x1 and x2. So those are going to represent, this one is going to represent the amplitude, this is going to represent phase. That's why I have taken the sum and the difference. You know how? If you cross check and carefully see what is the representation of electromagnetic wave, see it is having a and a dagger. Okay, so right, I think yeah, that's all. Okay, so this is the answers for your question, Rindamji, expression for the variances. Okay, right. So we'll take a 5 minutes break and we'll start about the gravimetry and some solid state sensors. Okay.
Okay, sir. Thank you, sir.